Welcome back to the FairScript channel. If you are new here, I'm Nikos. I'm the developer behind FairScript, a lightweight JavaScript library for finite element analysis in your browser. Today we are creating a tutorial video on generating meshes with GMesh and solving key conduction problems with FairScript. We'll start with a simple 2D rectangle, import mesh, apply boundary conditions, and solve it. Then we will add some complexity by creating a hole in the middle of the rectangle and solve it again. This builds on our tutorial at fairscript.com, so let's dive in. A quick recap: FairScript is an open source JavaScript library for finite element simulations in browsers or in Node.js. No heavy installs needed. It handles heat transfer and front propagation problems up to now. It's great for teaching, prototyping, or web integration. Today we are using its heat conduction module with GMesh meshes to simulate temperature distribution in a 2D scene. Head to fairscript.com for docs and examples. For those who are not familiar with GMesh, GMesh is an open source tool for mesh generation and post-processing. It's popular in the engineering community for quality meshing. We will use its own scripting language, the .geo files, for defining our geometries. You can download it from the website gmesh.info and follow along. Let's start with a simple rectangle, 2 meters wide by 2 meters high. Here's the gmesh.geo script from our tutorial. It defines points, lines, a surface, and physical groups for boundaries like bottom and top. We use LC for mesh density, recombine for quads, and finally set quadratic elements. We save it as rect.geo. We then run from the command prompt gmesh rect.geo -2 to get the final mesh. Here's the generated quad mesh with 30 elements. Now we will solve the heat conduction problem. Hot base at 200 degrees Celsius on bottom and right. Convection cooling on top with heat transfer coefficient equals to 1 and ambient temperature equals to 20 degrees. And finally we have symmetry on left. FairScript imports the .msh file and uses GMesh physical groups for boundaries. One key detail here is that GMesh uses one-based tags, for example the physical line 1 for bottom, but FairScript uses zero-based, so you have to subtract 1 to map the boundaries correctly. For example, the bottom tag 1 becomes 0 at boundary conditions. Local runs might hit coarse errors fetching the .msh file since are blocked by the coarse policy. A clean workaround is to host the mesh on GitHub Gist. Gist serves raw files over HTTPS. It's free, but you need, however, to have a GitHub account. In this tutorial, we built the heat conduction case entirely on CodePen. This makes it easier to experiment with. The mesh is imported directly from a GitHub Gist raw URL. We then apply boundary conditions using the physical tags, solve with LUsolve, and finally plot the temperature contours. Now let's add a circular hole in the middle, like a fin with a void. We will modify the .geo file. We will also add a new physical group. Now we rerun GMesh to get the new mesh. This example shows how FairScript can be combined with GMesh to simulate heat conduction on complex shapes. In this video, we walked through a full FairScript simulation workflow, generating a mesh in GMesh, mapping physical groups correctly into FairScript, running everything directly in CodePen, and finally extending the model by introducing a circular void. All of this runs entirely in the browser. If you found this useful, consider subscribing for more browser-based FEA tutorials. Also, don't forget to give the FeaScript repository a star on GitHub. In the description, you will find all the required files and also links to the CodePen demos. Thanks for watching and see you in the next one.